Building off of what we looked at with increasing and decreasing functions, we're now going to discuss what's called the first derivative test. So suppose that c is a critical number of a continuous function f. So if f prime changes from a positive to a negative at c, then f has a local maximum at c. If f prime changes from a negative to a positive at c, then f has a local minimum at c. And if f prime does not change sign at c, then f has no local min or max at c. So in our last example, we looked at finding the critical numbers for f of x equals x squared times ln of x, and we used that to find the critical numbers and then figure out which intervals things were increasing and decreasing. And what we saw was that the one critical number we had was e to the negative 1/2. And then we worked out that on the interval to the left of e to the negative 1/2, that we had negative values, and on the right we had positive values. So in the context of the theorem that we're looking at now, this e to the negative 1/2 is our critical number. And just by looking at the behavior from going from negative to positive, we can determine whether this is a local min or a local max. So looking back up here, if f changes from a negative to a positive at that point c, which is what we have here, then f has a local minimum at c. So because as we go on the number line left to right, we go from a negative to a positive, we would expect that this e to the negative 1/2, we would have a local minimum. And if we go back and look at the graph, or remember what the graph looked like, we'll see that. So as we look at our graph here, we see that at that point, at that e to the negative 1/2, that we do in fact have a local minimum there, and then it goes increasing again. And that's what the first derivative test is telling us, without necessarily having to look at a graph or even plug in values for the actual function itself. We can just use the derivative to determine whether it's a minimum or a maximum, at least locally. So let's do a problem here where we'll use the first derivative test to find the local minimums and maximums for g of x equals 4x cubed plus 3x squared minus 6x plus 1. So the first thing I want to do is find the critical numbers for this function. So I'm going to start by taking the derivative and setting it equal to 0, because that's how we find those critical numbers. So g prime of x is going to be 12x squared plus 6x minus 6. We go ahead and set that equal to 0. We get 12x squared plus 6x minus 6. Now everything here is divisible by 6, so we can go ahead and simplify this. This will just be 2x squared plus x minus 1. And if we were going to try to factor this, we could probably do so. So if we look at this, we get this will be 2x, and we'll have an x there, and I need a plus 1 and a minus 1, and I think I would put a minus 1 here and a plus 1 here, that this will factor properly. So once we know that, we have 2x minus 1 equals 0, or x plus 1 equals 0. So this tells me that my critical numbers are going to occur at x equals 1/2 and negative 1. Now, remember, we don't even care necessarily what the values are. We just care whether or not they're positive or negative. So we can work with this. So what we want to do is, what I'm going to do is draw a number line, and I'm going to write those critical numbers in here, negative 1 and 1/2. And what I want to do is I want to pick a test point from each one of these different intervals that we have in this problem. So I want to pick some point that I can easily test the derivative and determine whether that derivative is positive or negative in that interval. So I'll rewrite our derivative here. So g prime of x was 12x squared plus 6x minus 6. So in this green interval, I want to pick a number between negative infinity and negative 1. Negative 2 seems appropriate to try here. So if I do 12 times negative 2 squared plus 6 times negative 2 minus 6, well, we'll get 12 times 4 minus 12 minus 6. And this is going to be positive. We're going to have 48 minus 12 minus 6, so I think we're going to get 30. So that's the important takeaway here, is that this is going to be positive. The derivative is positive from negative infinity to that negative 1. Now I want to pick a test point between negative 1 and 1/2. 0 is a convenient point between negative 1 and 1/2, so let's go ahead and evaluate there. So if I plug in 0 here, we get negative 6. So on that interval, the derivative is going to be negative. And now for the last one, I need to pick something between, in this blue interval, from 1/2 to positive infinity. 1 is a convenient number to pick there and test. So I can do g of 1. And so we'll have 12 times 1 squared plus 6 times 1 minus 6. And if we go ahead and do that, we get 12. And so we get that it's positive here. So now, according to the first derivative test, if it changes from a positive to a negative at that point, then we're going to have a maximum. And if it does the opposite, we're going to have a minimum. So in this first one, we go from a positive here to a negative here. So that tells me negative 1 is going to be a local maximum. And then from at 1/2, we go from negative to positive. So that tells me at 1/2, I am going to have a minimum value at these things. Now, we haven't done any graphing. We haven't even used the original function other than to take the derivative, but yet it's given me all sorts of information about the graph of this function. So when I graph this, I'm going to expect to have a maximum when x equals negative 1, and I'm going to expect to have a minimum when x equals 1/2. Let's go ahead and check this. So as we go ahead and analyze the graph here, we see that at negative 1, 6, so when x equals negative 1, we do in fact have that local maximum, and when x equals positive 1/2, we do in fact get that local minimum. And based on this theorem, these are going to be the only times in this graph where we're going to have those local minimums and maximums. And we didn't have to look at the function itself once we took the derivative of it.